on our host for today, Dr. George Mason. Dr. George Mason has been a part of ISTVS for a long time. I guess I don't even know how many years. See, that's something he has to tell me. He's worked for the U.S. Army Corps of Engineers. Waterways Experiment Station was what it was known as. But now it's ERDIC, Engineering Research and Development Center, for more than 30 years. After that, he also joined CAVS at Mississippi State University, and he worked there for some time too. So he's seen a lot of stuff in mechanics, and I think he's also worked on DEM. So he's I guess a good host for today. So thank you, Dr. Mason, for hosting this session. I'm going to give it up to you now.
Okay, thank you, Varsha. I'm going to introduce Dr. Bohumir. He's a physicist, PhD from Mississippi State. He also has a strong background in European education. His degrees are from Mississippi State, and he has been working on discrete element modeling now for over 20 years, to my knowledge. He did some of the early work at ERDC, the research branch with the Corps of Engineers, and now he's up at the Center for Advanced Vehicular Systems at Mississippi State University. If you will, as he briefs, if you could ask questions in the chat, just bring them up, and we'll try to talk through the questions at the end of the session. That way he can expediently go through all his slides. I will also mention there is a MAGIC conference, so this is a good precursor to that. And MAGIC conference out of the University of Wisconsin, and it deals with the DEM research area and a lot of the advancements. So without any further ado, I'm going to turn it over to Dr. Bohumir. Professor Bohumir.
All right, thank you. Greetings to everyone from Mississippi. Thank you, George and Varsha, for kindly introducing me and for your help to set up everything before this presentation. It is my pleasure to present about discrete element method simulations for vehicle mobility in soft soils. This work was performed at the Center for Advanced Vehicular Systems, Mississippi State University. I will start by introduction with motivation for this work. Then I will present theoretical background for DM modeling, contact models. After that, I will talk about the DM simulations of an 165/60 R13 wheel in sand using coarse-grained DM particles. I will start with experimental reference for the simulations, which are measurements of wheel performance in sand under forward-only slip published by Shinone in 2010. Then I will clarify DM model selection and compare DM results with the experimental reference. Then I will present our most recent DM study on the same wheel with added side slip. I will also illustrate velocities of particles and wheel rim and show calculation of stress profiles at the wheel-soil interface. At the end, I will briefly summarize our earlier work on implementing coupled discrete element lattice-Boltzmann representation of shear thickening of particle suspension in fluids, and also another earlier work on calculations of soil stresses using fine-grained in-house discrete element model for a calibration chamber, cone penetrometer test, and for tractive performance of another larger wheel in soft soil. Accurately predicting wheel performance in granular media is essential for evaluating off-road mobility in architecture, in agriculture, construction, space exploration, and defense applications. Empirical relationships require resource-demanding experiments, and their validity is limited to the slip and speed ranges at which the measurement was performed. Finite element models have a hard time dealing with large discontinuous deformation of soil, especially under high slips and aggressive maneuvering. The discrete element method, on the other side, aims to model wheel-soil interactions with higher fidelity. However, For perfect physical representation, tracking every particle in fine-grained soil is computationally demanding. Therefore, DEM needs coarse-grained models. Stress profiles at the wheel-soil interface are sufficient to determine soil reaction to the wheel load. Therefore, the numerical representation is examined here. In our recent core-grained DEM studies, we applied Hertz-Mindlin and Hertz-Mindlin with JKR models to represent DEM contact physics. Hertz-Mindlin is the default model used in Alter's EDM software package due to its accurate and efficient force calculation. Note that Alter was recently purchased by Siemens. In the contact model, the normal force is a function of normal overlap. E star is the equivalent Young modulus, adjusted according to Poisson ratio of the materials in contact. R star is equivalent radius. Additionally, there is a damping force, FND, which is proportional to relative normal velocity. E is a coefficient of restitution. Beta will be used on the next page, and Hertz-Mindlin JKR model denotes a Hertz-Mindlin model with non-zero Johnson-Kendall-Roberts cohesion coefficient, which is further described in EDM documentation. The tangential force depends on the tangential stiffness and overlap. Here, G star is equivalent shear modulus. Additionally, there is a tangential damping force. It is proportional to relative tangential velocity, which is limited by Coulomb static friction. Experimental reference for the present DEM simulations was a study titled Experimental Analysis of Tread Pattern Effects on Tire Tractive Performance on Sand using an indoor traction measurement system with forced slip mechanism. It was published by Shinone et al. In 2010. It was partly presented at the 16th International Conference of ISTVS in Turin in 2008. Their study shows tread pattern effects on drawbar pull, gross tractive effort, running resistance, and sinkage. We compare with their smooth wheel results. The table here shows the dimensions of the wheel and the particle bed. The figure on the left illustrates the triangular facets forming the smooth surface of the wheel. The wheel has a diameter of 535 millimeters and the width of 170 millimeters. The figure on the bottom right shows facets for the particle bed, which was 3 meters long, half meter wide, and 60 centimeters deep. 3 yellow spheres show a single DEM particle. A particle bed to simulate wheel-soil interactions was generated using particle factory functionality of the Alter's EDM software. The particle bed was assembled from 5 identical material blocks, repeated along the longitudinal direction. To lower the simulation time needed to populate the bed with particles, only the particles in a single block were settled under periodic boundary conditions. GEMM stands for Generic Eden Material Model Database, which is distributed along with Alter HyperWorks EDM Discrete Element Method software package. The materials examined in the present work were selected using Material Wizard by answering 3 questions. First, the small application scale was chosen. It selects the smallest particle size available in the GEMM database, giving a mean particle diameter of 25 millimeters along the particle widest dimension. Therefore, we are using much larger mean particle size than the dry sand to reduce the computational cost of the model. 25 millimeter mean particle size is 5 times larger than the upper boundary for the particle size of coarse sand, which is defined as 4.75 millimeters by the cement concrete website. After selecting the smallest particle size, the material properties were chosen to match the bulk density and angle of repose of dry sand. The material wizard then offered 10 DM materials matching the selected material properties and particle size. Resulting GEMM material wizard table showing 10 rows with 10 wizard selected DM materials is shown on the bottom right. Full list of DM parameters for these 10 materials is shown next. Here, P indicates particle-only properties, PP indicates particle-particle interactions, and PG indicates particle geometry interactions. The particle bed, that means particle bed walls, and the wheel are considered geometries. There is a total of 10 material parameters. 4 of them vary among the selected materials. Those 4 are coefficient of restitution, or coefficient of static friction, coefficient of rolling friction, which is non-zero only for material number 1635, and JKR surface energy. Non-zero JKR is used to represent cohesive materials. Next, we describe the DM simulation procedure. With a load of 980 newtons, which corresponds to the load from the experimental reference, the wheel was placed minus 1.3 meters away from the center of the particle bed. By coupling a rigid wheel motion solver to EDEM, the wheel moved at a constant circumferential velocity of 97.6 millimeters per second to the final position of 1.3 meters. With a single degree of freedom, the wheel moved freely only along up-down direction, allowing sinkage to reach equilibrium. This animation shows the wheel motion at 54.8% slip in material number 1111. 1 times real time means that both the animation and the actual wheel motion completed within approximately 58 seconds. The range between the blue and red boundaries is about 5 centimeters, corresponding to the sinkage or rad depth of approximately 5 centimeters. What are the properties that are of interest from DM simulations? First, the slip is defined as a ratio of axis rotation over overall rotation. This slip is either forced or is calculated from the simulation, depending whether we are doing forced slip simulations or towed condition or self-propelled condition for the wheel. Drawbar pull force, which is a horizontal force available to pull external load, is defined over here. Then there is gross tractive effort, which is torque exerted by particles on the wheel divided by wheel radius. And there is a motion resistance, which is the difference between these two. The averages of these properties are calculated starting after the wheel and soil reach the steady state. The applied wheel slip ranged from minus 5.9% to 54.8% in both experiments and DM simulations. Time evolution of sinkage, net traction, and gross traction are calculated and recorded at each time step. Plots for the GM material 1636 and 45.8 slip over the full span of the simulations are shown. Initial data outliers are due to the wheel dropping from above the soil surface. The quantities are averaged over multiple time steps of the simulations. The averaging starts 7 seconds after the wheel begins moving forward to allow the soil wheel system to reach a steady state. The averaging stops when the wheel has traveled 1 meter from the center of the box, avoiding effects of the ending box wall. These plots show a comparison of drawbar pull force from DEM and measurement by Shinnon et al. 2010. The measurement results are shown on the red curve with diamonds. The thick black curve, which is the results from DEM material number 1111, was the best match to the measurement. The match is excellent for positive slips and slightly worse for negative slips. The gross tractive effort from the GM material number 1111, black, matched the measurement, which is shown in red, only for large positive slips. The best match to the measurement of the gross tractive effort was achieved by the material number 1311, which is the thick yellow curve. Note that the results from material 1301, which is shown by the gray curve with triangles, are always very close to the results from the material 1311. These two DE materials differ only in the coefficient of restitution. The best match to the sinkage measurement, shown in red, was achieved by the material number 1311, which is the gray curve with triangles. Again, the yellow curve is very close to the gray curve. The next best match to the sinkage measurement was the thick black curve from the DE material number 1111. This table shows R-square values, the coefficient of restitution, coefficient of determination between the 10 DE materials and experiment. The values of R-square close to 1 means the match is closer. The best matches are shown in green. The material 1311 matched the sinkage better than the material 111 at lower slips. However, the material 1111 predicts sinkage more accurately at higher slips, very high positive slips. These plots show average particle velocities. This can be compared with particle image velocimetry results. Top row shows negative slips of -40, 26.6, and 5.9%. Bottom row shows positive slips of 4%, 21.6%, and 45.8%. The velocities of particles were averaged over multiple steps of the simulation, starting 7 seconds after the wheel begins moving forward. This was done to allow the soil wheel system to reach a steady state. The averaging stops when the wheels traveled 1 meter from the center of the box, avoiding effects of the ending box wall, as mentioned earlier. Note that in the bottom row, the color scale is half-sized from 1 centimeter to half centimeter. And the arrow size scale is twice larger. That is because average particle velocities are lower for positive slips. The forward velocity of the wheel center is indicated by the topmost black arrow. This arrow is not shown, it's shown a little bit lower than the wheel center for a reason to save the space. The rim velocities are indicated by the 3 arrows on the front, rear, and bottommost point of the rim. These are the rim velocities. Normals to the rim velocity vectors intersects at the instantaneous center of wheel rotation, which is below the bottommost point of the wheel for negative slips and above for positive. The next slides will reveal how rim velocities are obtained. Notice there is a large discrepancy between normal component of rim velocity and particle velocity. For example, here, and the small arrows here. This can be attributed to lateral particle displacement due to the wheel being relatively narrow. It will be interesting to see these plots for a wider roller-like wheel covering the entire box width. These plots show velocities of the points on the wheel rim for a horizontally traveling rigid wheel with the slips of -40% and 40% in 0% and 40% in individual rows. -40% is the top row, 0% is the center row, and 40% is the bottom row. In the left column, the total velocity vector, green, is obtained as the sum of forward velocity component, VF, that is characteristic for the wheel motion, and the rotational component of the wheel velocity, VR, is equal to omega r, which is the rotational motion of the wheel. The middle column shows the same velocity vectors. However, a normal line, green, to the total velocity, also green, is drawn. These normal lines intercept in the instantaneous center of the wheel rotation. We can see that for negative slips, that is when the wheel is in skid, the instantaneous center of the wheel rotation moves down below the wheel surface contact point. For positive slips, the instantaneous center of the wheel rotation is moving up, close to the center of the wheel. For 100% slip, the instantaneous center of the wheel rotation would be in the center of the wheel. Equations on the right-hand side show classical Becker-Janoshi models. Janoshi model calculates the shear stress from accumulated shear deformation, which is obtained by integration of the tangential velocity component, shown as red arrow in the plots in the last column. These are cycloid curves that show trajectories of the three selected points on the wheel surface for -40, 0, and 40% slip. For 40 and 0% slips, the height of the instantaneous center of the rotation can be obtained by drawing a normal line to where the trajectory is vertical. For the positive slips, some points on the wheel move backwards. For negative slips, all points on the wheel move forward. These plots show contact forces and arrows, and normal and shear stress profiles and green and red curves. Contact forces and stress profiles are shown along the wheel contact with soil for 3 prescribed slip values and in towed and self-propelled conditions. In all the plots shown in this presentation, the wheel moves from left to right. Prescribed slip conditions are achieved by enforcing forward velocity and keeping the circumferential velocity of the wheel equal to 97.6 millimeters per second. With prescribed slip, the wheel is only allowed to move freely in the vertical z direction. The towed condition is achieved by forcing Vx, forward component of the velocity, with the value of Vc, circumferential, and by allowing one extra degree of freedom, free angular velocity omega y. That means the wheel is towed with a speed of Vx is equal to Vc. The self-propelling condition is achieved by prescribing circumferential velocity of 97.6 centimeters per second, and by allowing another extra degree of freedom, which is free horizontal velocity Vx. The slip can be calculated as average over the steady state of the wheel-soil system. The largest black arrow in these plots show the total force exerted by soil subgrade on the wheel. Its vertical component balances the wheel weight, which is 980 newtons. For the self-propelled wheel, the largest black arrow points in the vertical direction. Wheel just self-propel itself. The red arrow shows the sum of the shear forces exerted by soil on the wheel. Red arrow. For the towed wheel, the total area on the red curve is 0. Because the torque is 0. The red and green arrows add up to the large black arrow. The upper row plots here show normal and shear stress profile along the contact patch. Those are the previous plots, but they are just straightened up. The lower row plots the relative velocity of soil particles at the wheel-soil contact surface with respect to the wheel circumference. The velocity of the particle centers relative to the nearest wheel surface is also shown. The transition from negative to positive shear stress corresponds to the transition from negative to positive relative velocity of particles with respect to the wheel surface. The entry and exit angles were estimated by fitting the normal stress profile to the squared tilted sine function, which is shown above the plots. In addition to entry and exit angles, this function has a single parameter, t, that depends on slip. The t determines the level of tilt. Phi1 and Phi2 are the angles at which the wheel enters and exits the soil. The squared tilted sine approximation offers an alternative to connected halves of Gaussian distribution that was used by Hiroko and Ishigami in the Journal of Thermomechanics 2020. The shear stress profiles in the present plots resemble those measured by Hiroko and Ishigami. These plots include results from additional DM simulations for material number 1111 at large negative slips. Such a large negative slips were not examined by the reference measurement of Shinone 2010. The upper left plot shows wheel-soil angles for varying slips. The blue curve shows angle of maximum normal stress. The green curve shows entry angle, and the red curve shows exit angle. These angles were calculated from square tilted sine fit to normal stress. Ratio of the maximum to entry angle is approximated as linearly dependent on slip by Wong and Rees in 1967. This study does not support such approximation except for large negative slips. The lower left plot shows maximum normal shear stress for varying slips. The slip with the shortest contact patch, that is, the entry minus exit angle, produces the largest maximum normal stress. The contact patch length tends to increase for negative slips and also increase for positive slips, and is shortest for close to zero slips. The plot on the right side shows the dependence of sinkage on slip. Extending the simulations to large negative slips allow to observe the decrease in sinkage for large negative slips. DEM results are obtained by averaging of 50 to 500 simulation snapshots. Example snapshot from a single time step is shown here. The purple arrows represent individual particle wheel contact forces, demonstrating randomness of the values that are being averaged to obtain normal and shear stress profiles. The origins of purple arrows are located at the contact points of the wheel with soil particles. The green arrows are velocities of particle center of masses. These being far away from the wheel particle contact points is a demonstration of how large the particles are. The green arrows in the upper mid portion are velocities of particles that are in contact with the side of the wheel. The forces associated with those contacts, purple dots, are lower than those from particles contacting the wheel circumference. As a logical next step to simulating a wheel with forward-only slip, additional simulations with added side slip were implemented. This helped to determine cornering performance of a wheel in soft soil. The side slip simulations were performed using two DEM materials, number 1311 and 1111, which showed the best match for forward-only measurement. Side slip simulations were conducted over a range of forward slip of -5 to 54%, with side slip angles of 3, 6, and 12 degrees. Side slip simulations are similar to forward slip simulations, except that the side slip is introduced by changing the wheel orientation. The angular velocity orientation was also changed in accord with the wheel orientation. These animations are also displayed in 1x real time, meaning that both animation and measurement will take about 25 seconds. The range between the blue and red colors, which correspond to 25 and 33 centimeters, is about 8 centimeters, resulting in a sinkage or rod depth of about 8 centimeters. These plots compare the forward pull Fx to gross tractive effort, My/R, and sinkage results between materials number 1311 and 1111 at different slips. Varying slip is shown on the x-axis, and 3 different plots show value for different side slips. The measured value is also shown. However, that one is only available for zero side slip. Fx is the forward component of the resulting soil wheel force. The forward component here means pointing along the box longitudinal direction. The forward component of the drawbar pull, Fx, decreases with increasing side slip. Material 1111, with static friction lower than the material 1311, produces less forward pull and more sinkage at each side slip. The gross tractive effort, My/R, is lower for lower friction material 1111, pointing out even higher losses when wheel operates with higher sinkage. The most significant change in all three variables, meaning forward pull, tractive effort, and sinkage, is seen when the side slip changes from 6 to 12 degrees, that is, between the yellow and blue lines. These plots compare lateral force, shown as Fy, overturning moment, shown as mx over r, and self-aligning moment, shown as mz over r between the two materials. The side slip force, Fy, increases with the side slip angle as expected. The same is true for the magnitude of the overturning torque, mx, and for the magnitude of the self-aligning moment, mz, the self-aligning moment having much lower value than overturning torque. A significant change is seen in all three variables, even when the side slip changes from 0 to 3%. In conclusion, the DM study enabled detailed analysis of sinkage, traction forces, and lateral loads, revealing trends consistent with experimental data. By illustrating DM strengths and limitations in capturing tire-solid interactions, this work aims to support its use as a powerful tool for advancing vehicle design and simulations. Now I will briefly present our earlier discrete element method related work. These are snapshots from coupled DM lattice-Boltzmann simulations of particle suspensions in fluids. The top left animations is from 2D simulations of the drafting kissing tumbling phenomena, showing also fluid flow patterns. The animation in the center left shows the fluid flow patterns and the forces exerted by fluid on particles. The snapshots on the bottom left show particle suspension in fluid settling under gravity. The right side plot shows the work by Daniel Johnson, published in the Journal of Rheology in 2017, simulating shear thickening of particle suspension in fluid, reproducing experimental results for parallel play rheometer. These figures show results from fine-grained DM study of mobility compenetrometer performed at Center for Advanced Vehicular Systems, published in 2019 in ASC Journal of Geotechnical and Geoenvironmental Engineering. Close to realistic simulations were produced, including effects of stress field and soil density. Effect of confining pressure was tested by applying a vertical surcharge load at the top of the specimen. DM simulations allow calculation of the stress in soil based on interparticle and particle geometry contact forces. The animation on the right shows time evolution of radial stress during calibration chamber compenetrometer test. Snapshots in the upper right shows stress ellipsoid in the RZ plane, indicating both principal stress ratio and principal axis rotation. The equation on the left shows how the stress is calculated using DM contact forces. The plots in the upper row show laterally averaged contours of vertical stress under the wheel. The plots in the lower row show laterally averaged contour of shear stress. The braked -20% slip condition is shown in the first column, the towed condition in the second column, and the powered 20% slip condition is shown in the right column. The plot in the lower row shows a familiar butterfly pattern of the shear stress. These calculations are results of fine-grained DM study of tracting performance of wheel in soft soil that was presented at the 2021 ISTVS conference. The upper figure shows lateral variation of vertical stress under the wheel in braked, -20% slip, towed, and powered 20% slip conditions in kilopascals. Front view of the wheel is shown. Brake values are from a lateral section passing through the wheel axis of rotation. It is inclined 10% forward from the downward direction. The lower figure shows variation of normal stress along the contact patch in braked, minus 20% slip, towed, and powered, 20% slip conditions. The wheel travels in the left to right direction. An increase in the maximum value of normal stress for narrow contact patch was observed similarly to what was seen earlier. The contact patch length tends to increase for negative slips, as indicated in the earlier plots as well. Conclusions. In the recent study, we examined tractive performance from 10 materials from Alter's generic EDM material model database, matching macroscopic properties of dry sand. GM material number 1111 provided the best agreement with laboratory measurements reported by Shinone et al. 2010. Net traction was the most accurate model, except that slightly lower values occurred at negative slips. Sinkage was overestimated by up to 25% for slips lower than 40%, and underestimated by up to 10% for slips higher than 40%. The cross-traction agrees well with DM results for a slip larger than 40%, while at lower positive and negative slips, the cross-traction is overestimated by up to 200% at low slips of minus 5.9%. Thank you for your attention.
Thank you, Bohumir. I think we had some questions in the chat box. Varsha, some of these folks may want to ask these questions in person. I guess I can start the ball rolling by asking if you ran this with GPUs or CPUs when you did the experiment. And did you use graphical processing?
These simulations were quite slow. Some of those longest ones that were running at high slips, that means wheel was moving forward very slow, took more than 12 hours. We were also very conservative with time step because we wanted to achieve the smooth curves and no dependence on the time step. The time step was chosen to be 5% of the Rayleigh limit instead of 20% that is recommended. So unfortunately for this case, we did not use GPU. For these cases, we did not use GPUs. We only use CPUs. Fine-grained simulations, they had few million particles. They were done earlier on using in-house DM code. Those were using parallel HPC resources, but only CPUs. Alter HyperWorks allows to use GPUs. The computers that we were running the simulations on, or that we have available, did not have the GPU units, although we tested that Alter HyperWorks EDM was able to detect GPUs and worked very well. Unfortunately, we didn't have these resources available for the present research. Most of the stuff is focusing on AI, I believe, these days.
Okay. I see. I was going to ask about parameterization of the soil, but I see you use the cone index. I'll go to the next question. How did you prevent the particles from flying outside the box in the domain region?
So, these simulations, or the driving style of the wheel, was not aggressive enough to initiate the particles flying out. And also, we were fairly conservative with side slip angle. It was just 3, 6, and 12 degrees, where the particle getting out of the box was not really happening. If few of them manage to get out, which we did not actually notice, it may not affect the results a lot. Sometimes this kind of phenomena may be happening due to too long time step. If the particle penetrates the wall or the wheel too deeply, then it will result in one step, in a single step, and there is a high speed of particle or high speed of the wheel in a single step, and it may result in very large forces. So the phenomena of particles flying outside the box could be caused also by having not sufficiently small time step. I think that's all I can say about this.
Okay, we're going to go to the next question. I pronounced the name Setua Magua. Anyway, the data showed quite dynamic. The data was quite dynamic when you plotted it as a function of time, probably indicating there was a good bit of scatter. How did you plot the data versus slip ratio? I'm sure that's they're asking about torque or net traction. How did you calculate the average at a certain slip? And do you have did you have to run multiple cases to reach a steady state slip?
Very good question. So there is really a lot of noise in this data, and that is mainly due to particles being large and contact appearing quite suddenly, and disturbing the wheel motion. Now, all that we were doing is averaging. So we measured, the measurement was performed every 0.1 seconds. So we ended up averaging the values of torque, forces, and sinkage from about 50 to 500 snapshots of the simulations. And these snapshots, to make sure that we are already in the steady state, and that would be in, okay, I will return to the later. So we started only, I believe it was 9 seconds, I mentioned that, after the wheel was dropped into the soil box, started averaging, and we ended averaging quite a good distance between from the final wall. So we assume that from those values we can have a pretty good average that is not affected by the initial or final discrepancies that are due to wheel not being settled or steady state between wheel and soil not being reached. So those values that are shown in those big Excel plots, they are really averaged from the long time for each sleep. So we are actually running simulations for each prescribed sleep. That was the first stage. Exactly, we force the sleep. That was by prescribing the forward velocity and angular velocity of the wheel. Angular velocity all the time constant, and forward velocity is increasing to achieve the lower sleep. And so that means those are the certain sleeps, and we calculate averages at prescribed sleeps. And then when we add 1 degree of freedom, we can calculate the sleep just naturally from allowing the wheel to move either freely at a forward speed, that's a self-propelled condition, or when we allow the wheel to move with arbitrary angular velocity, that is the towed condition. We just prescribe the forward velocity. So we did not run the multiple cases to reach the steady state. We just assumed that the steady state was reached after those 7 seconds or 9 seconds from the start of the from the wheel being dropped into the box.
Okay. You showed 200% slip. Do you have the calculation of how you determine slip, or how you calculated slip? The equation for slip?
So let me, right. The slip in this work is calculated as excess rotation over, oh, I forgot the acknowledgement. I'm so sorry. Okay.
I don't mean to put you on the spot, but ISTVS has a definition for slip, and we don't all adhere to it.
In this case, it is the slip is calculated as excess rotation of the wheel surface. Excess, that means angular rotation minus forward velocity, divided by total rotation. In this case, maximum slip that can be achieved for forward moving wheel is 100%. So I believe we have values of 58 or so. Now, if we want 200% slip, the wheel would have to rotate and move backwards. That's the way we would achieve that. But we did not do rotate forward, but move backward. We did not do that. Here, I also wanted to show, starting from 7 seconds, maybe up to 50 or so, depending on the distance from the end wall. The averages were calculated, and we assume that this wheel states between in that interval is fairly steady. And now, let me see. Did I forget to answer anything?
Well, was the slip calculated as a function of intervals of time or distance? I guess it was a function of intervals of time.
Mostly as a function of velocities.
Okay.
Something happened to my, let me see. Can you hear me still? Great, thank you. I have a warning. Okay, thank you. Mm-hmm.
Sorry, again, I see where Z is. Somebody's mentioned that slip is, especially at 0, is not well understood, and that's a correct statement. I agree 100% with that one. Barsha, were you going to say something?
Oh, no, I was just going to say, yes, we could hear you, Dr. Jelinek. Don't worry about that. But yeah, I do agree with that statement.
Okay. Which statement?
With the slip especially at 0, that it's not very well understood. Different people have different definitions, and sometimes it gets to me too.
Yes. We're on the same page. Yes.
So ambiguity may arise from how do you define wheel diameter, whether it's usually there is effective rolling diameter. Right.
Yeah, that's also one more thing. Yep. I recently went down that rabbit hole because I was seeing different papers and how they were defining their slips, and yep.
Yeah, maybe that's a good target for the tire modeling community or workshop or group.
Yeah.
Look at different definitions.
Yeah, I agree.
Well, okay, I don't see any more questions. I see somebody typing in. It looks like there's somebody typing in one comment. Barsha, do you want to close out?
Yep. Okay, so slip is poorly defined at 0, omega, and we. was the comment that
I
was
see.
getting typed in.
That's a right. When you have 0 in the denominator, then there
Yep.
is a problem. So we are only looking at the wheel that rotates at least a little bit. Yeah.
Yep. ISTVS, I think, defines one for positive slip, another one for negative slip, where they flop the numerator and the denominator. I think positive is 1 minus V by R omega, and for negative, it's 1 minus R omega by V. So we probably avoid that. So, yeah.
So that bounds everything by 100% plus or minus.
Yep. Plus or minus 100%. That's true.
But I don't think beyond that there's a good rationale. So the idea of other definitions, I would agree that they need to be included.
Yep.
And I think everything's a function of time. They increments of time.
Mm-hmm.
And so if you change that definition when you get down to very high resolution, you might have to come up with new methods of computations, or at least different types of equations.
Yeah.
And at zero slip, the fun just begins if you're trying to figure out if there's actually traction net or gross traction at zero slip. Everybody has an opinion there.
Yeah, I agree.
But Varsha, I'll let you close it out.
Okay. Well, that sounds good. Well, that was a good session. Thank you for your amazing work, Dr. Bohumir. I think you were long due for a DES, honestly. And honestly, DEM is one of those techniques that I think our society is really interested in. It's given really promising results, especially for coarse-grained materials and things like that. And I've seen you always. I've seen a lot of papers from you, even Dr. George Mason. I guess collaborations too between both of you about DEM. And it's nice to have you guys here talk about the simulation world, because yes, and again, one more thing that you did was also compare it to experiments. And I think you were very transparent with the results that you had, and you explained this is what you get. And I think I really appreciate you doing that. So thank you so much for your presentation. I'm going to go ahead and wrap up this event. Of course, we talked about the research grant, the small research grants, the next ISTVS DES that we have, the working groups that are going to be active, I guess. And of course, the conference, the 2025 conference that's happening. I sent out all those links. At the end, I just want to say thank you for all the people here in the audience for attending. We do have a lot of stuff going on here at ISTVS. So please do subscribe to at least our emailing list, so that you get notifications from us. And also join our society. Honestly, we would love to have you guys there, support us, and also probably be a part of these events. So that's probably it. I'm going to be closing out. Thank you everybody for attending.